Wave energy is an opportunity bigger than all the nuclear capacity of the world today or all the hydro capacity. When you're a surfer and going to the beach and we feel as a surfer there's no waves, there's usually still a meter of swell. And there's not a bad energy content in that. I'm Patrik Müller. I'm co-founder and CEO of CorPower Ocean. So it is a big sphere, a big boy, which is oscillating up and down and side to side in the waves. The type of wave energy converter, it's called a point absorber. We put the device in optimal timing with the wave, and when we do that, we get a strong amplification. So like in a 1 meter wave, our devices move 3 meters up and down. We get somewhere between 3 and 5 times as much power per square kilometer. If you compare it to offshore wind, there is a clear path towards 40-50 euros per megawatt hour.
This podcast series at the Hack Summit is sponsored by 8, a design agency run by Gabri Grassi, helping impact-driven tech companies reach more people, attract investment, and scale further. Get your free, ready-to-scale brand checklist at the link in the description, together with a playlist of all other Hack Summit resources. If you want to elevate your brand, reach out to Gabri Grassi at the link in the description. Well, let's talk about wave energy. So first of all, I want to understand how you get started with a project like this, because, I kind of think about the solar panel, the big wind farms. It's like, those are like kind of massive projects from the get-go. And from a startup perspective, it's quite difficult. How do you get started with that?
Yeah, of course. Wave energy is another one of those really big opportunities. So, we're talking about an opportunity globally bigger than all the nuclear capacity of the world today or all the hydro capacity. So it's a big one. And then, of course, to attack something like that, in our view, at least, you've got to do it in a fairly structured way. So we've gone quite stage-wise and really gone to demonstrate first principles physics to start, and small teams, small machines, etc. And that's also why it's taken us 14 years to go through 5 stages of product demonstration to have something we're confident now is reliable, survives the biggest storms, and produces a large amount of energy compared to the size and the cost.
How do you test a product like that? Obviously, like the conditions in the sea are so difficult to work with. So like, how do you manage to kind of do a first test?
Yeah. So when we started back in 2012, we went around Europe and asked people who had been testing wave energy. I got into it coming from the semiconductor manufacturing field and was a little bit lukewarm in the beginning, to be honest, because everything you had heard and seen about wave energy was mostly quite big failures, catastrophic ones, a few of them, that had a lot of attention. And we felt that if we're going to get our time into this and start really going deep, we need to understand what people have done and learned before. So we went around Europe. So we went to Trondheim, we went to Lisbon, we went to Edinburgh, places where most of the testing had been done. We asked everybody who'd been trying, and very smart people have tried for decades and maybe 100 years, and if you look at it really, to make wave energy work. And we asked them what has worked and what hasn't. And common theme, I think, was that many people had a good idea and then felt that, okay, we need to get some money in, get some investors in, and then were kind of forced or fooled or didn't think about it hard enough. And they probably, in many cases, had too aggressive timelines, asked for too little money, too little time, and then had to build a full-scale device in that very harsh ocean environment that you mentioned, and then got out and then failed quite badly. So that had kind of been the history back in 2012 when we got started. So we decided quite early that if we're going to give this a real shot, we got to be very structured. And we said we need to improve the structural efficiency of wave energy by somewhere 5 to 10 times, meaning how much energy can you generate per the amount of equipment. Take energy per ton or energy per volume, which are good proxies for cost efficiency in volume, right? And then we set out a structured program where we started. So coming back to the question about testing, small devices this big, scale 1 to 50, 1 to 30.
And can you maybe quickly describe what the device looks like? Because I think for people that haven't seen the videos across social media, it looks quite fantastic. I love it. But can you describe it for me?
Yeah. So it is a big sphere, a big boy, which is oscillating up and down and side to side in the waves. The type of wave energy converter, it's called a point absorber. It means that it's a fairly small, round, circular device that then emits circular waves when it's radiating, moving up and down in the waves. And then we are translating the motion that the buoy does into rotation in a gearbox, and then generators inside, and then exporting that into grid compatible electricity coming out of it.
That seems quite simple when you explain it.
It is quite simple. There's a few inventions inside of it, of course. Yeah.
Okay, so first device, you started with a very, very small buoy. What's the size of it?
So this first one were maybe 30, 40 centimeter. And I didn't say that. The full-scale devices now are about 10 meters in diameter, about 100 tons of material in each one, and rated currently to 330 kilowatts. And if you then compare that to historical wave devices, they have been in the sizes of, let's say, 20 to a few hundred meters and thousands of tons of material for the similar type of power rating. So it is a factor 10. But we started in tank testing, small devices, went to different university labs, and then did a lot of benchtop testing. We started at the Royal Institute of Technology in Stockholm and did testing of the drivetrains, the gearboxes, all the mechanical, electrical components on the inside, and started small. And thanks to the tank testing, we could get proof point of a 5 to 10 type improvement. And based on that, said, okay, that's motivating us to start as a somewhat smaller or bigger device and a larger team, etc. And then we did that, another round of testing in France, in École Centrale Nantes. And that took us over to 2015. We started in 2012. And then by that, we built our first integrated wave energy converter, which was a half-scale machine that we deployed at the European Marine Energy Centre in Orkney, Scotland. So by 2018, we had a proof point on a half-scale machine. We had then spent about 6 years. We had not invited VCs yet, so we started and decided that we need to get us to a fairly solid proof point before we invite investors into this company.
How much money have you spent in the first 6 years? Do you remember?
What was it? Was it?
Or an order of magnitude?
Yeah, I think it was somewhere 6 to 8 million or something like that.
So very efficient.
Yeah. We were not too many people. Maybe we're closer to 10 towards the end, somewhere around there. And we were small teams at the beginning, reasonably small machines, worked a lot with universities where we could, if you say, borrow labs and equipment, been very lean in not investing into infrastructure, etc. And still keep a quite lean, capital-light business model overall.
I love that. When we think about the role that wave energy can play in the energy system, what exactly are we trying to achieve? Does it work with solar and wind? Does it replace solar and wind? Does it work with nuclear? Like, what's the role that you want to have CorPower play in that entire system?
That's a very good one. So, I mean, for us, the purpose of wave is to help balancing the mix. So on the big oceans, let's say the Atlantic in our case, you have weather systems from winds from US, Canada, Greenland, which is fetching up the swell content in the waves. And that's a process that takes a few days. That means that you have several different wind systems interacting and contributing to some kind of smoothening process. So when you pick up the swell on the coastline of Europe, let's say the Atlantic coast, Portugal, Spain, France, Ireland, Scotland, Norway, prime markets here in Europe, it's already firmed clean energy you're picking up. So you've stored the winds, so you can see the ocean as one of the largest batteries that we have in that sense, storing it. And then you pick it up, and when you add it to a mix of wind and solar, in order to achieve 24/7 clean electricity, typically the effect when you add wave is that you can halve the amount of installed capacity, you can thereby halve the amount of grid, and typically the amount of storage batteries that you need might go anywhere between 20 to an 80% reduction depending on the site.
Oh, wow. That's a massive reduction.
Yeah.
How do you work today? Is it like you do a project for specific industries? Do you want to connect to the grid as just an energy provider? What's the strategy?
So we're working today both directly with off-takers, so that might be industries that have the need to run consistently and they have an ambition to go to 24/7 clean, and also with data centers. It's a very attractive group of customers because there is a huge need to grow and there's some willingness to pay to actually be clean all around the year, 24/7.
Yeah, and they also don't care so much about the cost of power. I mean, they do to some extent, don't get me wrong, but they have massive budgets for that, and they're also very, very profitable.
Yeah, speed is the whole thing on that, exactly. But we also exporting to the grid, so we are seeing wave energy becoming a large, mainstream energy source in national energy systems over time. But of course, we're trying to start with customers that have the real need for it, the strongest one.
Is it running? So, I mean, I think one of the specificity of waves is even during nights you have waves. It doesn't depend so much on the weather, but maybe help me understand, what's the predictability of like how much power you can produce? Because I would imagine, I mean, I'm a surfer, so I sometimes go to sea and then there's no waves. And so like what happens if that's the case for you as well?
Yeah, that's a funny one. So when you're a surfer and going to the beach and we feel as a surfer there's no waves, there's usually still a meter or so of swell. And there's not a bad energy content in that. So I would say there is essentially no 0 hours in a year.
Okay.
The base is still quite reasonable.
Okay.
Our devices produce full power at around 3 meter waves.
Okay.
And in a 1 meter, there's still a significant production, even though less than a 3 meter, of course.
And 3 meters is small for the middle of the sea? Because, I mean, 3 meters, when you're on the beach, that's actually quite fat waves.
Yeah, 3 meters is reasonably big. I mean, you're maybe getting somewhere around 2 or so as an average, 1.8 to 2 in a typical Atlantic
Okay.
site.
So you need a minimum of like 1 meter, so to say, and that basically does the work.
We start producing at 1/4 of a meter.
Okay.
So one of the key things with our devices is that they're very efficient in low waves. So we have added, if you talk about our inventions, we've added something called phase control to wave energy, which means that you control the timing of the device with the incoming wave. So we put the device in optimal timing with the wave. And when we do that, we get a strong amplification on the motion. So like in a 1 meter wave, our devices moves 3 meters up and down. So it looks like it's jumping in and out of the water. And when we do that, we can extract a much larger amount of energy, typically 3 times, compared to the same buoy without phase control.
Do you need power to do that? Like to kind of move the buoy?
And the 3x is the net energy
Okay.
gain that we talk power gain that we're talking about in this case. So it does consume a little bit of power to
Yeah.
put it in optimal phase,
Yeah.
but the net gain is about 3x.
Okay. Okay, so it's not as simple as to say we're going to put a buoy in the sea and then it's going to produce energy.
Yeah, and the other big challenge that has been there is, of course, to survive the biggest storm waves. It's absolutely brutal out there. So our current full-scale machine, the C4, it's installed in the Augusta Dora site in northern Portugal,
Okay.
just north of Nazaré,
Okay.
where you have the biggest waves in the world. And it's seen 18.5-meter waves in the biggest storms it has been in so far. That means that the whole thing is submerged in the peak of the wave. And how we have solved that over the years is a transparent storm survival mode, meaning that this amplification that I describe in the regular waves is absolutely reversed. So probably the most important invention that we brought to wave energy is this transparency mode. So when the waves go above 6.5, 7 meters, we put the device, or it puts itself into a protection mode. And there it becomes, you can say, essentially transparent to the waves. So it's not reacting to it. So when you have like an 18.5-meter wave, the device moves maybe 2 decimeters up and down. It's essentially standing still, not
Yeah.
reacting to the wave. And that's how we've been able to survive the biggest waves at the same time producing a large amount of energy in regular waves. So it's like tuning and detuning the device.
Okay, so you still have this kind of concept of turning on and off, even if it's in the sea.
Yes, it's very similar to the wind turbines pitching the blades.
Interesting. How is it locked in a specific space? How do you make sure? Because if you have a wave that's 18 meters, it's probably quite strong. And as a result of that, I would assume that maybe the buoy is going to move. Maybe, and if the buoy is moving, then you have 100 tons buoy in the sea moving across the ocean, which is not, good, I guess, for like navigation and other things. How do you do that properly?
Yeah, so we use in sandy seabed, which is the most common in the places we're at. We use a special type of anchor. It's a pile that we drive into the sand using a low noise vibro driving technology. It takes about 20 minutes. We drive it 15 meters into the sand, and at the bottom of this pile, there's some secret sauce that we have patented, etc. So we have some IP also on anchoring these days. So we drive these piles into the seabed, then we lay the cables that connects in the future hundreds or then thousands of devices together in arrays that we call CorPacks. And then you tow out the devices from your port, and then you connect them to the anchor and the cabling. And we use a quick connect interface on the seabed. So it both mechanically locks in and then connects power and communication over fiber.
How long does it take to deploy one buoy? Or how does it work, first of all? Is the goal to have the biggest buoy possible to produce the most energy, or is it to have a set of smaller buoys all across, let's say, a location that you have designed?
Yeah, so we do believe that the cost optimal size is close to what we have today, about 10-meter diameter device. And that means we might get this power rating up towards 400, maybe 500 kilowatts over time. And they won't get bigger than that, because if you make them bigger, it's just that the loads and the forces, they keep growing, but the power falls off the curve.
Okay.
And that means you get less competitive technology. So our scaling model is very modular. So instead of doing bigger and bigger machines like wind has followed, the device size we have now is the one we are starting to do 45 of in the next commercial farm that we have. Then we're going to start deploying a few hundreds and then a few thousands of them. So it's much more like battery cells or solar PV, where you define your Lego piece, your module, always being the same. And then you get cycles of learning and economies of scale of doing the same thing on and on.
Do you need a permit to operate? How do you manage to secure, let's say, a piece of the ocean, so to say? Because that's what you need, actually, in order to put these buoys in. Because, if you have, let's say, 50, 100, 1,000, then it starts to take a bit of space, I would assume, right? So how do you manage that?
Yes, it takes some space. However, even though our machines are small, we put them in high-density clusters, so about 150 meters spacing. And that means we get somewhere between 3 and 5 times as much power out per square kilometer of ocean space if you compare it to offshore wind. So small machines, high density still is a very small use of ocean space. Having that said, we need permitting, and in each country there's a different regime. We have gone through that in Scotland with something called Marine Scotland, where you apply for a marine license, which we have had and have for a new farm there. Same thing in Portugal. We have something called a TUPEM, which exactly gives you the right to use a certain area of the ocean in the coming 10 or 20 years. And then there's an environmental study that you do related to that. And then you apply for the permits to have grid connection and be able to connect to the grid. And so once you've done that.
So the entire process from the beginning of we want to do this project all the way to we are producing energy, how long does that take?
I mean, a 2 to 3 year project development time is possible in the best places, where from when you start investigating which sites should we use, why this and that, and so on, until you actually start the project development, until you can be at final investment decision. And then from that point on, it might take 2 years to construct it, fabricating the devices themselves, and then a year to install and commission the farm.
How do we do that as a startup? I mean, obviously you can raise capital from VCs, that's great, but it's also like very long timelines, even just to deploy a project, not to mention the technology development and R&D that went into developing the project. How do you do it?
I mean, basically, so we are not the asset owner. So CorPower follows a reasonably asset-light model. So we are the OEM. So we are offering our customers, the energy companies or the power producers who own the farm, that we help them to develop it during the DevEx phase of the project. So we help them to design, lay out how you do the anchoring, the cabling, help them with all the permitting. So we get some revenues from engineering services during the design phase. That keeps us alive. And then once we get to financial close with the customer, who they are generally then responsible for the financing package of the farm, then we get the orders on the equipment. We start the fabrication with our supply chain, and we use a fairly distributed supply chain across Europe. The advantage of having devices of like sizes of 10 meters being our biggest dimension, you can use a lot of existing fabrication outfits across Europe. So we fabricate a lot in Southern Europe, Eastern, Central Europe. It comes to an assembly line, which we also use a contracted assembly partner for our devices, and then we ship it to the site. And then the big 10-meter hull, we have local manufacturing on site.
Okay.
So that's a technology we own and we have invested in. It's a mobile manufacturing cell, so additive technology where we're weaving up the composite hull locally on site, and we're now automating to take that to a 48-hour cycle time. So being able to churn out a composite hull every second day.
Wow. Okay. Fantastic. I guess if we go back to your story, which bottleneck has been more painful to you? Because obviously when you start this project, you can think, okay, engineering and doing a great brew is going to be the problem, but you also have permitting, certification, financing, manufacturing. What was the biggest problem that you faced so far?
Yeah, probably the biggest challenge for a project like this, if you just look at the chances of success, if you sit there on the first day and you're looking ahead saying it might actually take 15 years until we're fully industrialized and you can start deploying with a bankable technology, which we are now getting very close to. I guess just the going concern of a company like that is always going to be tough periods. You're going to have delays. You're going to run out of money. You're going to have challenges technically in the ocean. Something might just break or take longer. Also, so running out of money, I think, probably is the biggest risk in all projects like this. So that is one. And then, of course, just getting people excited and build the credibility in a new technology where nobody have succeeded historically. It's been, of course, a huge challenge as well. A big educational thing of actually showing people, well, look at the physics, look at the numbers. This is really, really scalable to a super competitive solution.
Yeah.
But getting people to look deep enough to see that, it's a challenge when you're doing something very different compared to how things have been in the past.
Do you have the feeling that you're forcing a technology to market?
Not at all. There's a huge demand for 24/7 clean solutions right now. It's probably the strongest. I mean, what's happening around us, again, is just a very harsh reminder that as long as we're dependent on fossil fuels, and we are, at least half of the time, we're burning stuff.
Yeah.
When it's not windy, when it's not sunny, and there's a painful reminder on that again. So I think that the demand and the desire to find solutions to affordably, I must say, get to 24/7 clean is big. And I guess there's a few options. There's geothermal, there's wave energy, and then that will always be combined as well with different forms of storage, lots of storage as well. So I don't see that we are fighting to try to push the technology into market, but I would say that from when we started, the view on wave energy, because of the history, has been like before you get into a room with an investor, before you finish the word wave energy, they ran out of the room kind of. And that's not at all the case anymore, because now we have a lot of proof points, but that has been the challenge along the way.
Do you think the opportunity is as big in wave energy as it is for like geothermal or kind of, I had recently a mini series with Energy Impact Partners where we talked about in 5 different episodes about fusion level bets. In other words, fusion level like technologies that could deliver such a big outcome.
Yep.
We haven't talked about wave energy in that series. Is it as big as that?
Yes, it is. And it is possibly more proven today. Okay, it's hard. You got to be very in depth to know exactly what challenges is remaining for the different projects in geothermal. But my understanding is that the proof point we have now in wave is quite solid. We don't need to invent anything new. We don't need to prove anything new. For us, it's just repeating the same thing with less complexity, less parts, and lower cost, and doing lots of it. It's truly a scaling journey, where I understand in geothermal there's still some technical challenges being worked on. Fusion, not to mention it, or SMRs for that part. Like, this is a technology that is ready to scale now.
How many megawatt do you have delivered so far?
So currently we have 3 machines. So we have 1 installed in Portugal full scale. We're adding 2 more this year. That takes us to 1 megawatt. And then we are working very hard now to get to financial close on the first commercial projects that should happen in the second part of next year. And that is then in total 20 megawatts. So it is 45 machines in Portugal and 15 machines in Orkney, Scotland.
What's the cost of one machine?
Currently, they are a bit more than a million and a half, and they're going to come down towards the 500,000 euros per machine over time. Perhaps a bit lower than that, also in big volume.
I'd love for you to tell me a bit more about the economics of this business. You obviously said, you need to be bankable. I'd love to dive into what that means. But if we take the entire kind of cost structure of a project like yours, and then the revenue structure, which is more, the cost of energy or like the price of energy that you're producing, what does that look like? What are the big components?
Yeah, I mean, it is, of course, the on the cost side, it's the machinery itself, and then it's the anchoring and the electrical export network. Maybe the electrical infrastructure is about a quarter of the overall capex, and the remaining.
Electrical infrastructure being like basically connecting the buoy to the grid?
Yes.
Okay.
So laying an export cable from an on-land substation, building an on-land substation, and then we have a collection hub. So our CorPacks, which is then a set of devices 10 to 30 megawatts, is then feeding power into a collection hub where we collect the power and then step up the voltage to where we export it, typically 66 kV to the grid. So that's the cost structure. The good part is that the majority of the capex in the early farms are dominated by all our custom-made components. So it's early days, right? So the ability to fall in cost is not just by volume or negotiating better with the supply chain. It's huge opportunities to simplify the designs, doing the same thing with less complexity, less parts. And that is the biggest driver to reduce capex. And then on the OpEx side, operating these, it's still a quite high cost in the early days of operations because you have, especially when you have small farms, you need a vessel to do it. You need your port facilities, etc. So you're amortizing quite a few fixed costs on reasonably few megawatts in early projects. And as soon as you get bigger projects, that comes down quickly. But one big thing we're doing in operations is we're now looking to design and develop together with partners remotely controlled vessel dedicated to bring our devices from the port out to the field, install it on an anchor position, go over to the next position, disconnect the buoy, take it back to port without any people involved.
Oh, wow. Okay.
So we're trying to automate that and make it remotely controlled to really make that a super efficient operation, and that drives down cost tremendously.
Does it? Because it seems like very shiny when you say it, but like, is that really the best use of your time and money?
I do think so. So, because we've developed this product over 14 years, and it's now to the numbers, the metrics in it is such that when you start making hundreds and then thousands per year of this, you come to very competitive cost of electricity, assuming that you can also install it with a high efficiency way and operate it. So this is the next frontier for us to really now, based on 5 cycles of operating and learning how to do it with more manual existing methods, you develop dedicated solutions that gets the cost of the operations down.
When we think about what you're producing, you're in the end producing electricity. So electricity has a price in the market, depending on which source and everything. But first of all, is that the main thing that you're working towards, which is just bringing down the cost of electricity? And second of all, where do you stand in that cost curve? Obviously, we know that solar and wind have had a tremendous ride, batteries as well. Yeah. They went down crazy over the last 10, 15 years. What about you? Where do you stand? Is wave energy going to have the same cost structure and cost curve, so to say?
Yes. So we're expecting our cost curve to be somewhere between wind and solar. Solar has had the most impressive learning rates. And that is largely due to this repetition of one defined unit, the Lego piece, that is just then more and more made efficient. So we expect to be clearly below 100, probably between 75 and 100 after having 5 to 600 megawatts deployed cumulatively. And after a number of gigawatts, there is a clear path towards 40, 50 type of euros per megawatt hour. Having that said, what we do with customers today is that we do a lot of energy system modeling. We use PyPSA typically as an open source tool that has higher credibility. And then we find together with the customers in a certain demand profile, in a certain site, what is the lowest cost 24/7 power mix that a customer can use. And what we find in that is typically that we can price wave energy 3 to 4 times higher than wind and then even higher than solar in most cases and still reduce the cost of the clean power mix for the customer.
Oh, wow.
Assuming that you're interested in going anywhere near 24/7 clean electricity, we're typically targeting like a 95% firming level or so in the beginning.
Yeah, that's the beauty of it. I think the beauty of that model actually, and the reason why it's so strong is that actually, while solar, for example, has a very big issue with intermittency, right? Like it's just there's no sun at night, and so what do you do during that period of time? And that's where I guess wave energy is coming to help the grid.
That's exactly it. And you asked before, like how predictable is it? You know, a few days is exactly in advance what's coming in, and is also over a week more or less a flat curve.
Okay.
Over the year, it's producing most in the winter and the least in the summer, which is also a perfect mix together with solar PV, which has the opposite annual
Yeah.
curve.
Can confirm as a surfer that during the winter the waves are bigger, for sure. Okay, well, look, we're getting towards the end of this episode, but I guess I want to kind of have a bit of your vision for the future because I don't think there are many players like CorPower today in the market. I think you're one of the companies that is the most advanced in the space. Not to put pressure on you, but you have this industry relying on you today. And so if CorPower fails, then maybe we're going back to, okay, wave energy is never going to work. What has to happen in order for CorPower to succeed and become this massive energy provider for the world with wave energy?
It's a pressure we're feeling, and we are working with the sector quite a bit, and we're very friendly with more developers because we want 2, 3 companies that are about equally good,
Are
right?
you alone today?
We are the leader for sure.
Okay.
And there's a handful other, mainly European companies that are working very hard to get to the same kind of proof point we've gotten to already. So we're sharing them very strongly from in the sector, and we work very actively in the sector and try to collaborate to build something big. But to come back to the question, what do we need to scale? So we need the first commercial projects to have a revenue support system or a capex support system from either national countries or the European Union to make them bankable and investable to equity investors and debt providers into the project SPV. So the first project that we now have called Viana Wave in Portugal, we have a 39 million euro grant from the European Innovation Fund, and we expect some help from Portugal as well in that one. And with this, we can offer a reasonable return on equity for investors coming into the projects, etc. So we need that capital structure to work on each stage. So, and the one we're doing now, the first commercial ones, small 10 to 15 meg, is the toughest. The next, we need maybe half of the capex in public support on the very first projects to be bankable. The next one, we might need 30, 25%, next one 15, 20%, and then quite quickly it goes to zero. So the aggregated help we need is somewhere, let's say around 3 billion euros for an energy technology, and that it can be distributed on all the European countries and EU, and that's nothing. Like
Is it?
then we're having a self-propelled energy technology that is just rolling out on the market without any help. One offshore wind farm is getting that kind of support. Like Norway just issued for a floating wind farm of 500 megawatt a grant of 3.5 billion euros. That's exactly the amount we need for all our farms. So yes, it's not a big amount of money we need from public side to roll out.
So in order for you to succeed, you're still going to be relying a lot on public support for the beginning of the story.
You need some of them, but in the next phases where we're going to 50 towards 100 megawatt farms, the amount is actually coming down quite substantially. But we need some in the beginning, as any new energy technology. That's unavoidable.
It's interesting. One of the short question before we finish this episode, but what about China? I feel like they want to deploy every single type of source of energy that's possible in the world. And obviously, they're famous for deploying a lot of wind and renewables and solar. But also, when you look at the curve of like how much electricity they're producing, they're actually also producing more and more coal-based power and everything. So they're kind of just like pushing the button, everywhere on every type of energy. Have they started to look at it?
Absolutely, they have. So we're seeing and have been seeing quite a few devices looking like some developments in different institutes. What I would say in wind and solar, to a big extent, the Chinese market has gotten so effective by first iterating in a domestic market and then getting really the efficiency up and usually quite a competitive process between different manufacturers. And then some of them start exporting on the more global market once they've gotten to a level of maturity and competitiveness. In wave, there's not a huge wave resource in China. So there's hardly any waves. So I don't expect that it's going to become very competitive to deploy wave energy along the Chinese coast. And maybe that's a reason why that loop of domestic scale up won't happen to the same way it's happened in wind and solar. But you never know.
Yeah, I wouldn't be surprised if they were to launch something like that. Fantastic. Well, a few questions and short questions.
Mm.
What do most people still get wrong about wave energy today?
I think most people haven't understood the size of the opportunity. And secondly, people haven't understood that it's actually as proven as it is today.
Do you have a number to tell the size? How many gigawatts could we produce? Terawatt, maybe?
Yeah, so between 5 and 1,500 gigawatts. So that's like 2,000 to 4,000 terawatt hours.
What changed your mind recently about how this industry is going to scale?
Sorry,
What changed your mind recently about how this industry is going to scale? So, what have you realized recently that, you were not aware of when you started the company?
I mean, I think what we have learned along the way is the value of the power profile. That is probably over time when the cost of solar, for instance, have come down, the cost of batteries come down. Always, of course, we worried, do we have a role to play? But what we have learned over time is that the consistent power profile that fills the gaps is so valuable that we really have a role to play. And that's something that takes time to learn in very detailed energy system work.
Okay, and one last question for you today. How can we reach out if we want to support you by any means? What's the best way to get in contact with you guys?
You find us on CorPowerOcean.com, the webpage, and then, of course, on LinkedIn and any other channels there as well.
Love that. And then one last question, as always. Who's the next person that should be in your seats?
Yeah, who should be here next? Who's doing cool things? You got the wood tower manufacturers in Modvion.
Okay.
I think you can talk to them. Tidal Energy is, of course, our cousins as well in the ocean energy space. So there you have, for instance, Minesto, another Swedish company, or Orbital up in Scotland that are the leaders, among the leaders in that space.
Fantastic. Love it. Well, it was a pleasure to have you on the podcast, Patrick. Listeners, if you like this episode and if you like the show, don't forget to like, comment, and subscribe if you're on YouTube, or to give us a follow and a 5-star review on Apple Podcast and Spotify. Patrick, thank you so much.
Thanks a lot.